March meeting of the Royal Astronomical Society of Canada Ottawa Centre. This is tonight's program. We've got a pretty good program tonight. As you may recall, Kelly Jordan had to step down as our chair as her life has taken her elsewhere, so I'm going to be taking over for the rest of her term. I'm Oscar Echeverri. I'm also the club's treasurer. So I'll be running the meetings, accepting suggestions for speakers and topics. So please be sure to contact me. The email address that you can reach me at is meetingchair@ottawa.rasc.ca. We'll help you with the PowerPoint if you need any help there. But yeah, be sure to send me any suggestions or recommendations, comments, etc. So we've got some new members. Welcome to these three new members in February. Aaron Austin. And I'm going to hand the podium to Paul Foniger. He's as a tribute for our departed friend, Paul Comision.
Thanks, Oscar.
That advances the slide. Pointer back.
Sorry, you'll have to give me a second on my notes here. I usually just memorize what I'm going to say, but it's a little bit different today. Well, I wish I was up here on a happier occasion, but I am honored tonight to pay tribute to a dear friend and a fellow traveler in space-time. As most, I'm sure, are aware, our longtime club member Paul Comision passed away on February the 18th, just a couple of months shy of his 90th birthday. Paul was an avid astronomer and a dedicated member of the Ottawa RASC since 1979. He devoted a lot of time and energy to our club and served in numerous positions spanning many years. He was to us a councillor, a vice president, president, and even served as our national representative to the RASC organization. And last year he was granted the Ottawa Centre Service Award for his longtime devotion to our club. Paul was genuinely enjoyed serving in these capacities, and I think it was in his blood, because he was also a fourth-degree member of the Knights of Columbus, a high distinction within that international service organization, which he joined in 1950. But it was more than the noble desire that drove Paul. He had a truly deep passion for casting his eyes skyward and observing all that the universe had to offer. So much so that he built an observatory, his Omega Observatory, adjacent to his home in Barrhaven. He spent many, many nights at his beloved 14-inch telescope, hungry to hunt down the next object on his NGC bucket list. Paul was also an avid fan of the sun, making many detailed observations and sketches of sunspots using his solar telescope. He even continued this into his latter years, observing the sun through his living room window when it became more difficult for him to do this from the outside. But his greatest draw was the deep sky, observing star clusters, nebulae, and of course, galaxies. He challenged himself beyond the grand members of the Messier catalog that many of us are familiar with. And he cataloged literally hundreds of observations of very distant NGC, ARP, and ABLE objects. And he was certainly fascinated by galaxies of all sorts and shapes and sizes, and the interactions of groups and large clusters of these. In the last 10 years, he became involved in imaging, and so recorded many of these observations of these very obscure and distant objects, allowing him both to view these objects that he could never possibly see directly with his eyes, and also to share these observations with us here. The commish, as he was fondly known to members here that knew him well, was also a frequent contributor of images. But it wasn't just the images. Paul loved to do the research, understand the objects that he had spied, and then pass this knowledge on to all of us, giving us food for thought and putting the views into perspective. And when he couldn't see or image an interesting object or phenomenon directly, he applied that inquisitive approach of his to his famous cutting edge of astronomy talks. He read extensively on current astronomical research and discoveries, and enjoyed passing on what he had learned to us in these talks. He did this for 15 years and rarely missed a month. These are just some of the works that he had, that you've just seen from his collection. As I prepared this talk, I went through a collection which he gave me of his work there, and there are like 900 images of different objects that he had viewed and imaged in the last 10 years. God, I thought I was prolific. At his last talk at the club in December of 2004, the Ottawa Centre renamed the Observer of the Year Award to the Paul Commission Observer of the Year Award to honor his deep dedication to studying the heavens and sharing his observations with us all. I have to say that this is one of the things that I really admired about Paul. While he earned his BA in economics and business and worked for many years as an economist for the federal government, when it came to astronomy, he was completely self-taught. He had a real thirst for this knowledge, and he wasn't reluctant to ask when he came across something that he didn't fully understand. I remember many enjoyable evenings spent with him over the last few years when I offered to help him operate his observatory when this became increasingly more difficult for him to do. We would spend many hours into the early morning hours and talking on everything from galactic evolution, dark matter, dark energy, alien life, hyperspace, and numerous other areas of current astronomical interest. And I was always amazed at how alert and animated he was at his age at 2 in the morning. Most people, even a lot of people that I've joked with in this club, saying, I don't know how you do it after midnight on a bag of toys. Paul was there, and he just, sometimes no offense, Paul, but sometimes I couldn't shut you up. You're awesome. I often said to him, I have to admit, I often said to him that he was my hero in this regard, because I hope to be as keen and into this as he was when I'm in my 80s. Cross my fingers and hope that comes to pass. I have no doubt that if his body hadn't failed him, he'd still be keenly at his telescope until the sun forced him to shut down. Paul was eager to participate in RASC events whenever he could. He frequently joined our after-meeting meetings to chat even more astronomy. And last year he even submitted one of his favorite images as part of our astrophotography display at the Schenkman Art Gallery as part of our GA activities. It was his terrific nebula shot. I've read over the last couple of weeks quite a few wonderful tributes to Paul since his passing, and there's one in particular I'd like to share. I'm sure some of you have already read this or seen it, but in case you haven't, this was sent out by Mike Earle. Mike is a lecturer at the Royal Military College, former meeting chair of ours here, and a longtime acquaintance of Paul's. As you may have noticed in one of the previous slides, Mike was also the one that put forward the motion to have the Observer of the Year Award renamed in Paul's honor. He wrote us the following. With the passing of Paul Gregory Commission, a true giant of the Ottawa RASC, we have lost one of the greatest astronomers in Canada. He was great for not only his experience in the subject, but also for his enthusiasm and insatiable curiosity that was so infectious to all of us. He was a wonderful mentor to many of us as we learned about communicating the wonders of astronomy to large audiences and star party attendees. Paul was a rock of the Ottawa Centre, always cheerful and full of life. Paul's cutting edge of astronomy talk showed that he could appreciate the future of astronomy as well as what was already known. He always wanted to know more, which was such a wonderful motivator for the young and old alike. As I deliver my seminar a week from Tuesday, I will be dedicating the talk to Mr. Paul G. Commission with much respect. So long, my old friend. Nobody can possibly replace you. May your booming voice forever echo throughout the heavens. Thank you for sending this, Mike. I think it well reflects the feelings that many of us share about Paul, those of us that knew him well. And as a final gesture of generosity, Paul has also gifted his fully computerized 14-inch telescope to our center. With the ongoing rejuvenation of our Fred Lawson Observatory, as well as possible future developments elsewhere, I believe Paul's desire to share the cosmos will live on through his kind donation and touch members who didn't have the good fortune to know him personally. Paul's spirit is now set forth on his furthest exploration of the universe yet. May the winds favor your sails and carry you to distant shores. Fare long and farewell, dear friend, and thank you for all that you have given us. Thank you.
Thank you very much for that, Paul. Members in the news. We also had another member of the RASC pass away, Bill Day. Stephen McIntyre had his letter and image featured in Sky News. Congratulations, Steve. And this Saturday, March 24th, from 8:30 to 9:30 is Earth Hour. So be sure to turn your lights off, conserve electricity during that hour, and step outside and see if our light-polluted skies are any darker. Yes, the Observing Challenge. So this is something that I want to bring to the meetings every month. The way it's going to work is Gordon Webster and myself, specifically for this month and going forward, we're going to be picking a list of objects in varying ranges of difficulty, from beginner to advanced. And the idea will be for you guys to take note of the objects, make sacrifices to your deity of choice, asking for clear skies, go out, make observations on the objects and record them, and then submit them to the observers' reports for the meetings and to astronauts as well. So, our first beginner's challenge will be for folks to go out and find M44. So M44 is an open cluster in constellation Cancer. It's also known as the Beehive Cluster. For our intermediate challenge, it's going to be NGC 3079 in Ursa Major. It's a 11th magnitude galaxy. And as a bonus, for those with imaging rigs or large scopes, the twin Quasar is in the same field of view, and it's a gravitationally lensed quasar at 17th magnitude. And our advanced challenge will be PK 189 plus 7.1, also known as MINC 1-7, and it is a 13th magnitude planetary nebula in Gemini. We're also going to have a lunar challenge as well. And this month, we'll see if you can find the crater Thesis. All right, and with that, yes, they'll appear in Astronauts as well, and yeah, I'll get them posted up on the website. So Dave Chisholm isn't here today, so I'll cover his Ottawa Sky segment. The full moon is today. New moon is on the 17th, so fingers crossed for clear skies during the moonless period. Mercury is at greatest eastern elongation on the 15th of March. Venus is visible all month just after sunset. Mars visible in the early morning. Jupiter visible all night starting around midnight and as early as 11 p.m. later in the month. Saturn visible in the early morning. Uranus visible in the early morning or early evening all month. Neptune not visible at all. The ISS, the best viewing date is tomorrow. Is that right? Tomorrow? Yes. Doesn't have the time. Oh no, it does. 05:27. So in the morning. So there's the approximate path of the ISS through the sky. And another busy day at the British Henge sites as the staff work all day to move the stones forward by an hour. Again, daylight savings time coming up. Thank you for that, Dave. Okay, and with that, I'll give the podium to Al Scott for his astronomy news.
Thank you, Oscar, and thank you for taking on the chairmanship of our meetings. Looking forward to it. And thank you, Paul, for the tribute to Paul Commission. I know Paul has been a longtime friend and also inspired me with his cutting edge of astronomy to take on this 10-minute astronomy update after he stopped in 2005. So he's definitely an inspiration to all of us who knew him. So for the news today, combing the Hubble frontier. These are images from a data set called the Hubble Frontier Fields. And these consist of 6 deep Hubble images, like the Hubble Deep Field, of 6 different galaxy clusters and the parallel fields next to them. So you can see at the top, we have 4 of these galaxy clusters, very dense with galaxies. And in the bottom are fields nearby that aren't part of the cluster for comparison. And these are available for people to look through, and there's been a lot of work with citizen scientists going through these things and trying to identify interesting objects. In recent years, citizen scientists have combed the Hubble archive data, and I gave a talk a while back talking about green pea galaxies that were identified by people just looking through these images and finding these peculiar looking green pea type galaxies. They're luminous, compact, low mass, so less than 10 billion solar masses is low mass for galaxies, when the Milky Way is closer to a trillion stars, for comparison as a middling type mature galaxy. But they have high rates of star formation. That's what makes them look green. We can tell the star formation rate from the color of these galaxies and the distance of these galaxies. When stars are formed, we know they form in the main sequence in a particular distribution of masses and brightnesses and colors. And young star clusters typically have a lot of blue giant stars, which have very short lifetimes on the time scale of the universe. Tens of millions of years, they go supernova, they disappear. So you can tell how old a cluster is by looking at its color to a certain extent, and as they age they turn redder. So older galaxies are red and orange, younger galaxies are blue or green, and star-forming galaxies especially, galaxies that are forming a lot of stars, a lot of ultraviolet flux and blue flux. So not long after these green peas were discovered, other galaxies were also discovered that were even smaller, on the order of 3 to 30 million solar masses. And these span less than about 3,000 light years in size. And these were called blueberries for their distinctive blue color. Well, now scientists combing these fields have found an even higher star formation rate objects which are even lower mass. They call little blue dots. So this is a busy little slide. In the upper right here you can see the green pea galaxies that were found about a year ago. The bottom right are these blue dots, and the discovery images are along the top of along the top here. So these are what they saw in the fields, and by co-adding several of them they were able to get a better idea of their real extent to kind of disentangle them from the noise. And this is a graph which I will explain a little bit. So these blue dots are tiny blue objects, nearly point sources in the Hubble data. They discovered a total of 55 of these little blue dots with masses estimated between about 1 million solar masses and a few tens of millions of solar masses. But what's really interesting is the star formation rate. And so this graph here is a log-log graph. So this axis is the mass in solar masses. So a 6 means 1 million solar masses, a 7 means 10 million solar masses. On the vertical is the star formation rate in solar masses per year. So they estimate how fast these things are forming. So a 0 means 1 solar mass is being formed in these galaxies every year. Doesn't seem like a lot, right? But really, a star every year in a galaxy, which exists for millions or billions of years, can really put a lot of stars together. And these lines are specific star formation rates. And what this means is it's the star formation rate divided by the mass of the galaxy. So the 10 to the minus 9 means that it's going to take something like 1 billion years at that star formation rate to make up the mass of that galaxy in stars. This one, 100 million years, and this one, only 10 million years. So anything that falls on this line is going to make up all of its stars in 10 million years. It's an amazingly fast star formation rate. And these red, green, and blue dots are these little blue dots, basically. The color codes here are looking at the redshift, or Z parameter. This tells us how far away or how old they are. A Z value of 0 is present day. A Z value of 1 is something like 6 or 8 billion years old, and when you start getting down into the 2 to 5 regime, you're getting very close to the beginning of the universe, like a billion years after the formation of the universe, roughly speaking. So these are different age groups, these colors of objects that were found in the Hubble Deep Field. And the age is based on the redshift, which we measure by looking at characteristic emission lines in these galaxies, the Lyman alpha typically, and we know where it's supposed to fall in the spectrum, and we can see where it actually falls. It's shifted to the red, and this corresponds to the age based on the expansion of the universe. So you can see we have these different classes. These dots here are the blueberry galaxies that have been discovered previously from this study. And this is another class of little blue dots that are much larger and much slower in star formation. So they look like little blue dots, but they're not quite as blue as the really high star forming ones. So the interesting thing about this data, the intriguing thing, is that these little blue dots may be the globular clusters being formed. They're just about the right size and the right rate and the right age to become the initial globular star clusters that are collected in the halos of all the major galaxies now. Globular star clusters are about 1 million solar masses of gravitationally bound stars. Now, to get 1 million solar masses gravitationally bound, you have to build on the order of 10 million solar masses of stars and you'll lose a bunch because they won't all be gravitationally bound and they'll move off. So they figure that these particular ones could very well explain the formation of the globular star clusters, which is kind of an interesting discovery because people hadn't, up until now, observed early stages of globular star formation. So very interesting. My second item, revisiting an item from about a year ago again, the TRAPPIST-1 system. About a year ago, this red dwarf star was found to have 7 roughly Earth-sized planets in orbit around it. And all of them could be contained within the orbit of Mercury at the distances they are from the star. But because it's a much dimmer star than the Sun, they're not as hot as Mercury. In fact, 3 of them are in the so-called habitable zone, where they could have liquid water at thermal equilibrium on their surface. So this was a very intriguing discovery. People are now interested. Is it possible they could have conditions appropriate for the formation of life? So the Hubble Space Telescope had looked and stared at these things and tried to look and get spectra of them to see what their atmospheres might look like, and see, as they passed in front of the star, what wavelengths were absorbed by the star. And so the purple is, the purple lines or curves here are what you would predict if these were gaseous atmospheres of hydrogen, like the outer gas giants of Neptune and Uranus in our solar system. And the dots are the actual measurements that they made with the Hubble Space Telescope. And what this means is that in a lot of these cases, they've ruled out a hydrogen atmosphere for these objects, which means they're possibly like rocky planets, and they may have conditions what we would consider more conducive to life. So stay tuned, there's more information. These are TRAPPIST-D, F, E, and G. Previously, they'd already ruled out hydrogen atmospheres for B and C. So what this means is that none of these are Neptune-like objects. The Hubble data weren't clear enough to say anything about oxygen or water, but when James Webb Space Telescope goes up, they would be able to measure oxygen and water in the atmosphere as if they were there. So stay tuned for that soon. Another data point on the TRAPPIST-1 system. Here are the objects in the system, B through H. On this graph is the illumination from the host star, where 1 is the same amount of illumination that the Earth gets. Around 6 is Mercury. So these ones are getting a lot more temperature. These are the ones that are in the habitable zone, if you will, where water could exist as liquid, and these ones are probably frozen on their surface. But what they've been doing is doing precise timing of the transits now. Because these planets are all in a resonant chain, the inner one goes 8 orbits when the next one goes 5 orbits, they can measure small differences in their timings and determine from this not only their orbits, but their masses, radii, density, and surface gravity now. And what they've been able to do in this graph is plot their relative density relative to Earth. So here's the Earth's density, a nice rocky planet. And you can see planet E here is very similar to Earth. Same rocky density as Earth. Planet D, at the same kind of solar radiation as Earth, is only about 2/3 the density. What this means is this probably got a lot of water, a lot more water than the Earth. No more than 5% of the planet by mass, but that's 250 times more water than Earth would have. So very interesting results here that we have rocky planets, rocky Earth-like planets, and a lot of them, these ones are probably icy giants, so they're not as rocky as Earth. There's probably quite a bit of frozen water in them. And all of these ones also have a high volatile content compared to Earth, which is interesting. So the most likely volatile that we would think of is water that makes these less dense than the Earth. So these things probably have a lot of water in them, which is very interesting for the possibilities of life. So we'll keep our fingers crossed and watch out for more data on these things as it comes available. And I'm sure when James Webb comes up here, hopefully I'll be able to tell you more about it. Thank you.
Thanks, Al. All right, so up next, we're going to have a talk from Jim Thompson from the Imager's Corner. Next slide.
Good evening, everyone. Tonight I'm going to talk about something that you've probably heard many times in the talks about how to process images, and that is the idea of the histogram. This is a talk that we gave as part of our astronomy workshop series about 3 years ago, and I've regurgitated it here for all of you to enjoy. So, if you go and look up in the dictionary what a histogram is, you get the definition at the top. A graphical representation of the frequency distribution of a variable in a body of data. Kind of a dry explanation that doesn't really help you. But if we break it down and look at the frequency as the number of times something is occurring, the variable in particular we're looking at is the brightness or the color value in your image. And the data we're talking about is the image. So all the pixels in your image is the data that we're talking about. So let's make it very simple and look at this happy little image here that I put together. It's a 4-bit grayscale, so the pixels can have a value from 0 to 15. And I've limited it to a fairly small number of pixels, so it's easy to get a grasp of what we're talking about. So now if we examine each of the pixels and figure out what grayscale level they have, and then count them all. So of the grayscale level 8, there's 5 of them. Of the grayscale level 0, there's 8. And similarly for grayscale 15, there's 12. So I'm just counting how many of each grayscale level there is. And if you put that into a bar graph, that is a histogram. But you can see the number of black pixels, the number of gray pixels, and the number of white pixels. And that's all there is to it. So if we look at simple but a few more pixels, this nice 0 to 15, it's another 4-bit grayscale image. But it just happens that it has the same number of each color of pixel. There's 4 of each. And that's what the histogram would look like. So we'll go a step further and look at a more complex image. This is a picture of the Tycho Crater taken by the Lunar Reconnaissance Orbiter. And it's a 8-bit grayscale image. So there are pixel values from 0 to 255. So this is what the histogram looks like for that image. Along the bottom, we have a bin for each of the grayscale levels from 0 to 255. So depending on what the bit depth of your image is, you'll have a different number of bins. There'll be 16 bins for 4-bit, 256 for 8, and 65,536 for 16-bit. Along the y-axis is the number of pixels at each of those levels. So in the case of black, grayscale level 0, there are quite a few. There's probably about 200,000 pixels in that image are black. Now, most often in software that you use for manipulating or for collecting images, you'll see the histogram drawn simply as a line, but it's giving you the same information. So, what does the histogram tell us about our image? It gives you an idea of how the intensity of pixels is distributed. So how many dark pixels you have, how many light pixels you have, how many in the middle. And you can use this information to do things like figure out if you're losing information at the dark end or the light end of the image, which we call clipping. You can figure out if you are completely using up all of your possible colors, from 0 to 255 if it's 8-bit, or 0 to 65,000 for 16-bit. And you can also use it to tell how well color balanced your image is when you compare the histogram for each of the color channels. Now what the histogram does not tell you is where those pixels are distributed in the image. So for example, these two images on the bottom have exactly the same histogram. So I mentioned that the histogram is useful for figuring out certain things about your picture. The first thing is clipping, or saturation. So here I have an image that many of us would consider to be too dark. And that shows up quite clearly by data being shoved way over to the left-hand side. And you actually see there's a little roll-up right here where the data increases suddenly towards 0. That's a clear indication that we are clipping off data from the image on the dark end. Similarly, if you look at an image that's too bright, you get the same roll-up on the light end, showing that we are losing information from the image because it's too bright, it's saturated. Now, just like the story about Goldilocks, there is an image that's just right. And there you can see there's no roll-up at the ends. The data rolls gently down towards 0 or to some low value at each end. So that is a well adjusted histogram for that image. Now a similar thing with the dynamic range of your image. If you're collecting the data in as effective a manner as you can, if you look at an image that's kind of flat, the data looks kind of scrunched. I don't know if you know what I mean. So the peak in the middle is very pointy, and there's a gap over here on the dark end where there's no data. So all of these bits in our image data are empty. We're not making use of them. So this isn't an efficient use of our bit depth. Similarly, for an image that's too bright, the peak now you see is all stretched out, and there is clipping at either end. There's a little bit of a roll up here. You can't see here a roll up, but the histogram has a fairly high value by the time it gets to white. So that tells me that we're losing information off either end of the image. We're not really properly filling the bit depth of the image. And then the just right image have nice rounded peaks, and the data rolls down nicely towards 0 as we get to either end. Even this isn't quite perfect. There's a bit gap here, but it's much better than this one. So knowing this is very useful when you're collecting your data. I know when I'm collecting like the moon, particularly because it's such a large dynamic range object, having the histogram, the live histogram up on the screen in your software, you can very easily adjust settings to make sure that you're not losing any data, but you're also capturing as resolute a data set as you can. So a few notes on color images. It's exactly the same as for the grayscale images, except there is a histogram for each color channel. So if it's a red, green, blue image, a cyan, magenta, yellow, black image, or a hue, saturation, and luminance image, there will be a histogram for each channel. You can manipulate each of those channels independently of each other, which allows you to have a lot of control over the color balance of your image. And you can do false coloring, you can do all kinds of interesting tricks to pull out detail in your image. And that's something that I believe Paul is going to touch on in a later session of the Images Corner. The overall brightness of the image, called the luminance, in a color image, it's a weighted average of the color channels. It varies depending on the camera and the image type and everything, but it's basically a weighted average of the color channels. In the case of the HSL, HSL, which I don't know if many people edit their images in that color channel system, but the luminance is directly accessible in its own channel, which can be helpful during the editing process. So there are lots of tools available in software today to allow you to play with your histogram and make adjustments. They come with many different names. Brightness and contrast are probably the two most common adjustments you can make. But there's also something called gamma. There's tone balancing, tone mapping, and curves. They're all kind of similar. There's dark point, white point adjustments, and midpoint adjustments. They all kind of have different names, but they essentially do very similar things to the histogram. I'm going to go through a couple of the more common tools that are used. So first, brightness and contrast. So here's a range of images across the top. And I've adjusted the brightness just using a simple photo editing software. And you can see how the histogram changes as you go from dark brightness adjustment up to light adjustment. And it's essentially stretching the whole histogram. Pins the left-hand side, and as you increase brightness, it stretches the whole histogram to the right. Contrast is a little bit different. It's stretching the histogram, but it's stretching both ends at the same time. So you can push all the data together into a narrow range, or you can pull it all out to better fill the bit range of your image. And you can see what happens if you go too far. So in the case of the brightness, the data is starting to pile up at the right-hand end, and it's starting to clip data. And similarly with the contrast, I've pulled it too far here, and I'm starting to lose data, just starting to lose data off of the dark end, which is why we have black parts in the image. Another tool which is very handy to use, you've probably seen the term before when you're adjusting the brightness of your monitor, trying to play a video game or something, gamma correction. But it's a way of adjusting the way the midtones in the image are distributed. It doesn't change the dark end or the light end, it just shifts the whole histogram left or right. And as a result, you can make, depending on how the data is distributed, you can make the overall image look darker but more contrasty, or the opposite. So it's very similar to playing with the brightness, but it ends up not causing any saturation. As I said, the left and right endpoints don't change. So getting into a little bit more advanced tool that you can find in editing software, the tone balance. This is an example from the software that I use. You have three adjustments that you can play with. Shadows or a dark point, the mid-tone, and the highlights or a white point. And these are sliders that you can move around. You can move them together as a group, or you can move them independently of each other. You can also pick the channel that you want to work on. You can work on the overall brightness of the image, or if it's a color image, you can pick the individual color channels. It's your choice, what you're trying to achieve. So the black value, it says basically where you put this. It says, okay, from that point down is black, and and everything else gets kind of stretched accordingly. Similarly, if you adjust the white point, where you set it is where in the histogram is white. From there up would be white. And the mid-tone is basically the same as a gamma adjustment. So if I move the mid-tone slider down, more of the data is to the bright side of the midpoint, so it makes the image brighter. And similarly, if I move this slider to the right, more of the histogram is to the left, making the image darker. And there's many variations of this tool, depending on what software you're using. Now the fancy tool, well, maybe there's fancier ones, but for me the fancy tool is curves. It gives you the ultimate control over what your histogram looks like, and it's basically a map. So if this intensity level in your image, so all these pixels, you're saying, I want them to go from this value to this value. And so this line is a translation. So pixels over here, they get mapped to this value of brightness. Pixels over here, this level, get mapped, to this brightness. So right now it's a straight line, so it's a 1-to-1. So there's basically no changes being made. But if you start moving these little handles around, changing the position of this line, you change the way your data is mapped to the output image. So some of the examples are, if you move the whole line up, it makes the image brighter. If you move the whole line down, it makes it darker. If you make it more vertical, you're increasing the contrast. If you make it more horizontal, you're lowering the contrast. Now, if you adjust, you can add a midpoint. By default, there isn't always a midpoint here, but usually you can add one. And then you can start playing with that. And that's just like adjusting the midpoint in the tone tool before. And if you're really adventurous, you can add multiple points on the curve and adjust them all independently and get some really interesting effects. You can see the mapping here is quite weird, where all the bright pixels are mapped not too different, but the mid-range is being mapped much brighter. But the dark end is pretty much the same, so you get very interesting effects, highlighting different parts of the image, depending on how you adjust this. So this is maybe not the penultimate, but it's up there for tools that you can use. And you can achieve all the adjustments from the simpler tools, brightness, contrast, gamma, you can all do from this one tool. Oh, that's it. Any questions about the histogram?
What software do you use?
I am an antique, and I use something called Picture Publisher. It's very, very simple, but it has all the main tools that you need to use. Any other questions? I know we don't have a lot of time for this, but yeah, go ahead, Jim.
How do you manipulate contrast again? How are you using the midpoint? Are you adjusting the midpoint? Or
Using the curves tool, for example,
the previous
the
one?
previous tool.
The levels. The curves tool, that would be the levels. Would you?
So using the tone balance tool to adjust the contrast.
Yeah.
Anything you do to move the dark point and the white point closer together increases the contrast.
Oh,
And apart, with this tool you can't really decrease the contrast because there's nowhere to go with the sliders, but you can move the sliders closer together.
okay.
So for example, it looks like there's no data right here, or that it rolls off to be not a lot of data. So if I were to adjust my white point slider over this way, I increase the brightness, yes, but I'm also increasing the contrast because I'm now making the data fill all of the bit depth better. Okay, does that make sense? Any other questions?
Questions?
Okay. Yeah, if you have any questions, you can come. Oh, way in the back there.
Yeah. The histograms, the red histograms seem to have gaps every now and then. Why was that?
That often occurs when you have data that's collected at a bit depth lower than the file type. So if for some reason you're only getting 8 bits per channel and the file format you're using stores it in 16-bit, then you're going to see gaps. It has a lot to do with the analog to digital converter in the camera you're using, for example. Okay, we'll move on. I think there's one more slide here for me. April 21st, write it in your calendar. International Astronomy Day. How many people were here at the museum for the solar eclipse this summer? Raise your hand. Okay, did you guys have a good time? It's a lot of fun? Well, this is even better. It's an opportunity for us avid astronomers to share our passion with the general public and hopefully encourage them to also pursue the hobby of amateur astronomy, or at the very least maybe an interest in science in general. And it was all started by a group in the US called the Astronomical League. That's why it's in April when the weather's nice in California and not so nice in Ottawa, unfortunately. But every year, both the RASC and other observing groups in the Ottawa area put on a big public sidewalk astronomy event. It's a lot of fun, and I encourage anybody who is interested in participating, whether it's bringing a telescope out and sharing a view of the sky with the public, or just coming out to meet people and talk about astronomy, that you get in touch with some of the organizers. So the event that's held at Silver City in the Gloucester area is organized by me. You can contact me if you're interested in going to that. And I don't know if the RASC who will be coordinating with the museum this year.
Chris Terry.
Is it going to be Chris again? Were you just volunteered, Chris? So, and again, it's an observing event here, coordinated with the museum, and it's a lot of fun. Even if you talk to 1 or 2 people, or help a child have a look at the moon through your telescope, it's totally worth it. So I encourage you to make the time to come out to participate. And that's it. Thank you.
Great, thank you very much for that, Jim. All right, so now we're going to have our break, let's say about 10 minutes. We'll come back and have the rest of our meeting. We have door prize tickets here, or some door prizes that we've got to give away at the end of the meeting, so feel free to come up. And I'm told there are 8 copies of Astronotes here as well. Yeah, if you didn't get one, just go ahead and grab it. Okay, and we're back. So yeah, we're going to have Jesse Rogerson give us a talk on the nitty-gritty of astronomy, as he called it. Yep.
Okay. Is this too loud? Can you hear me? I'm not going to stand in the spotlight. I feel better walking around. Is that cool? Okay. I have a laser pointer.
You won't be on the video, though.
Oh, that's not me. I need help. Chris, help me.
The only slide you get, you're going to memorize the rest.
Yeah, good luck. So I'm Jesse. I work here at the museum. Oh, there's my talk. And just in case you're confused, as all of us are, we've been rebranded to Ingenium. So the museum's name didn't change, but our umbrella corporation changed. So if you ever see the word Ingenium anywhere, it's referring to aviation, space, ag and food, and the new Science Tech Museum. So that's all 3 under one. So I'm Jesse. Before I came here, I bounced around a little bit, but I was at York University for my PhD down in Toronto. And then I was out in Calgary working at Telespark, the science museum there. And then there was a brief time where I wasn't sure where I was going to be, and I ended up here. And I'll tell you where I might have ended up at the end of the talk, which would be really cool. But I'm going to take you through, for about half of my talk, what I did during my PhD at York with Dr. Patrick Hall, really great guy. I don't know if any of you ever had him for a talk. He's really great. And we worked on quasars together. Specifically, the title of my dissertation was Monitoring Broad Absorption Line Quasar Variability. Sounds super cool. But I'll take you through what it means and why we should care, and why I like it. Okay, so to set the stage, you have a galaxy. So here's a galaxy. I don't know the name of this one. I think it's a fake picture, or is it not? Does anybody know this one? Yeah, it's fake, right? Okay, good. So this is just I think it's what the Milky Way is supposed to look like, but I just picked it because I needed a stand-in galaxy, and it can be literally any galaxy that you are thinking of for the most part, whether it be elliptical, whether it be something like this, more like a disk galaxy, or what have you, or regular. The major galaxies are like roughly this big. So 100,000 light years, 35,000 parsecs, roughly speaking. 100,000 years for light to travel from one side to the other. And at the center of most of them, probably, we haven't gone and checked every single galaxy, but at the center of most of them is probably a supermassive black hole. Different from a regular-sized black hole, there's two kinds. There's stellar mass, which are like 10s, 20s, 30s, 100 times the mass of the sun, and supermassive black holes, which are hundreds of millions or billions of times the mass of the sun. At the center of our galaxy, the Milky Way, we have one, I think it's 4 million times the mass of the sun, and that's the supermassive category, and there's one per galaxy, or maybe two, depending on the state of evolution of the galaxy, whereas stellar mass black holes, there's millions of them, all over, because they're the result of supernovas. But one per galaxy, and I'm interested in those, and they can come in two flavors. Oh yeah, I need to mention this. So a really interesting thing about massive galaxies is that the mass of their supermassive black hole is correlated with the mass of the galaxy itself. So if you have a big, huge, massive galaxy, you have a big, huge, massive, supermassive black hole. And it shrinks. If it's a small galaxy, a smaller galaxy, you'll have a smaller supermassive black hole. So there's this weird connection that says something's going on during the growth of these galaxies, during the building of a galaxy, that shepherds the two. Whether one affects the other, we're not quite sure. We don't know what the causation is, but we do know that there's a correlation. We know that you can roughly predict the mass of a galaxy if you know the mass of its supermassive black hole at the center. Okay? That's really important. The two kinds of supermassive black holes you're going to find are these two, either active or quiescent. Active black holes or non-active black holes. Actively eating or not actively eating. Ours, at the center, Sagittarius A star, is considered not active. It's doing a little. There's some material that's kind of getting close and getting pulled in, and some dust sort of floating around, and it's doing a little bit, but it's not doing a lot. An active black hole, an active supermassive black hole, is like tearing apart stars and pulling it down and like really wreaking havoc. And I'm interested in the active ones. And because this is happening at the center of a galaxy, or the nucleus, if you have an active supermassive black hole, we call this an active galactic nuclei, or an AGN. But let's get way down into the center there, to what we think it looks like. So let's skip there for a second. We're going to put this in motion. So here is an active galactic nucleus, okay? So you have a black hole at the center, supermassive black hole, hundreds of millions or billions of solar masses, and a whole bunch of material trying to fall onto it. The black hole has torn apart gas clouds or stars or whatever. Whatever has happened, a whole bunch of material has been pushed towards the center, and it's trying to fall on, but not all of it can fall on at once, because there's stuff in the way. It piles up, and it creates a disk, what we call an accretion disk, and that disk gets very, very bright because of all that piling up. Oh, I want to go back to that. See if it'll let me. So stuff's piling up as it falls on. It squishes down into a disk because of conservation of angular momentum, and it gets really, really bright because of friction, because of the gas rubbing up against other gas trying to fall on. And if you're really far away from the black hole, the gas isn't moving that quickly, so the friction's not that high. And if you're really close to the center, the gas is moving really quickly and trying to really fall on and get really bright. And this is all happening, this is the crazy thing, this is happening on the scale of a parsec, less, or roughly on the order of the size of, it's not the size of the solar system, but like the order of the size of the solar system, roughly. Really, really tiny, but this whole disk of stuff, accretion disk, in a quasar, which is the brightest end of AGN, can be brighter than the entire galaxy itself. It can be 10 or 100 times brighter. That little tiny section of the galaxy can put out more energy than the whole galaxy of hundreds of billions of stars. Crazy. The difference between a normal galaxy with a black hole that doesn't have actively eating, or one that is actively eating, is this. The type of light that it's putting out. So you have the whole electromagnetic spectrum here along the bottom. Whoops. Along the bottom from X-ray out to radio, from high energy to low energy. And an active galaxy with an active galactic nucleus is going to be bright everywhere. It's just shooting out tons of energy all over the place. If there's no active nucleus, then you have this curve underneath, the purple curve there, the normal galaxy. Gives you just a sense of, they just look different. They are acting differently, even though that's coming from very tiny parts of the galaxy. For my work, I was only worried about UV. The UV light of the galaxy, of the supermassive black hole. The UV light of the stuff around the supermassive black hole. And if we zoom in on that, this is an actual spectrum in the UV light. So this is 1,000 to, well, it goes out to into the optical, but optical is like between 4,000 and 6,000-ish. So that's optical light. And so this is UV light. And I was interested in an even smaller section of this. I was interested in just this section of the spectra of quasars. And so of particular note is the Lyman alpha feature and a carbon 4 feature. I'm going to break this down a little bit more, but just pointing that stuff out. So here is that same spectrum, but I flattened it out. So I sort of took out the features, I divided out some features and flattened it out. Same idea though. There's parts where there's no peaks, and then there's these peaks. And there's specific elements at specific transitions making that light in these peaks. That's a regular broad absorption line quasar. Or sorry, that's a regular quasar. This is a broad absorption line quasar. And it is clear there's a difference. Here there are these big absorption features. And about 25% of quasars, just roughly, if you pick a quasar out of the sky, 25% of their spectra are going to look like this. I'll get into what spectra are in a little bit. So this is created, basically there's a really interesting, just on broad absorption lines themselves, where if you take the light of a quasar and you break it out into a rainbow, and you look at its UV spectrum, 25% of them are going to have these big absorption features. There's a noodle scratcher back in the 80s and the 90s. I'm going to back up a little bit. No, it won't let me. Okay. This is what happens when you convert from Mac to Windows. So I want you to imagine that accretion disk of material, which is really bright at the center and not so bright at the edge, as a flat disk. And if we look at it from the edge, so that's what this is. So, there we go. So flatten it out, look at it from the edge. You have the supermassive black hole at the center, and you have the accretion disk of stuff that's really flat and really long, and all of the light that's not creating the peaks is coming from that disk. There are, the emission features are coming from within the disk as well, but the bright light, the X-ray light's coming from here, the radio light's coming from here, and you have the rest of the spectrum in between. Really hot towards the center, not so hot towards the edges. The broad absorption features, the light that's being taken away, we think is caused by a wind something like this, where some material somehow lifts up off the disk a bit. Once it's lifted up off the disk, it then can see the bright disk that it was embedded in, and that light pushes the gas away. The light literally, the light from the accretion disk drives the massive wind flying away from the disk at ridiculous speeds, and I'll show you how fast it goes. And here's where this is key, breaking down what a quasar, a broad absorption line quasar versus a regular quasar. If you look at this object with this line of sight, you're looking at the continuum, you're looking at the black hole directly, you get a regular quasar spectrum. But if you are looking through the wind, then this stuff that's flying away from the disk is absorbing some of the light. And that absorption feature shows up in what we call a broad absorption feature. Does that make sense? All right. You're with me so far? This took a long time to figure out, but it was back in 1995 when it really got solidified. So I didn't have to figure that out, which is nice. Here's a really interesting thing about it, though. Because the wind is moving at a really high speed, this is how to say this? This is the carbon 4 feature right here. So carbon 4, and that's line and alpha. So carbon 4 that's sitting in this wind is going to want to absorb carbon 4 light that's emitted by a carbon 4 atom. So it wants to, basically, the carbon 4 gas that's sitting here wants to absorb this light. But it's not. It's absorbing the light just to the left of it. Just a little bit blue shifted. Just a little bit to the left. This is a silicon feature, and it would normally, if the light wasn't moving, would absorb light at exactly that. But it's a little to the left. And the reason for that is because because the gas is moving. It's moving towards the observer, which means it blue shifts the type of light that it's going to actually absorb. It blue shifts just a bit over, and it actually doesn't absorb exactly where it normally would have if it wasn't moving. It's a little weird to think about. But what the take-home is that this feature is the carbon 4, and the light that's being absorbed right here is moving at a speed to absorb at a different color. And it actually, to get all the way out here, that gas would have to be moving at 30,000 kilometers an hour, or kilometers per second. 30,000 kilometers per second. It's like insane. So we see this light being absorbed because it's moving towards us and absorbing carbon light from further down on the accretion disk here. Whew. It's a lot. But what this whole picture schematic diagram says is that there is gas traveling away from the black holes at 30,000 or more kilometers per second, which is way more than enough to get out of the nuclear region of the galaxy itself and into the rest of the galaxy, which means this is a way for feedback to happen. This is a way for the mass of a black hole to regulate the mass of the galaxy, or vice versa. This is a connection. This is a way to talk, because the gas is leaving the central region. Now here's I've almost got through my entire title. Broad absorption line quasars, but I was monitoring broad absorption line quasar variability. They change. This is where it gets really interesting. So this is the same quasar, observations taken pretty far apart, and look how the absorption features have changed over that time. So what does that mean if the absorption feature is changing every time you go look at it? It can be one of two things. It can mean that the gas that's coming at you is also moving tangential to the line of sight. So we're looking at the accretion disk, and there's gas moving across our line of sight while it's moving towards us. Or the gas could be just moving directly towards us, but the absorption features of the gas are changing. So maybe it's getting too hot, and so it can no longer absorb the light that it was absorbing before, so it stops absorbing it. what we call the ionization feature of the light, of the gas. So basically getting thicker or thinner to absorb the carbon light. But in general, what it's saying is that if a variability is observed, if a quasar's absorption feature is seen to change, it's telling you something about the wind itself. It's telling you something about the physics of the wind, how it's moving, where it's moving, and how its absorption properties are changing. So that's valuable information. And I wanted to monitor that. So there you go. That's my whole thing. So, to give you a sense of what I actually did, this is what we think a quasar looks like. This is a very much an artist's interpretation, because quasars are so far away that they are point sources. This is what it actually looks like. It's the same. A quasar is a word that came out of a short form, a QSO, a quasi-stellar radio object, because back in like the 60s when they were discovered, they were first discovered as radio sources, so bright radio sources, and then later on they attached an optical component to it, so they looked at the same part of the sky that the radio light was coming from, and they looked at it in optical, and they found these bright point-like sources in the optical light, and they looked like stars, because they're point sources, but their spectra look completely different than a star. So they called them quasi-stellar radio sources, or quasars. But they look like point sources, so there's one. That looks like a spiral galaxy of some kind. This is from CFHT, Canada-France-Hawaii Telescope. So what I did is I took that kind of image and I put a spectrograph on it, and I spread out the light. So this is the light. This is the light from that point of light right there. So you take that light, put it through a prism, spread it out into a rainbow, and boom, that's what that looks like. Does anybody know what these lines are? Some of you might. They're skylines. Our sky gets in the way sometimes. So this is a rainbow. It doesn't look like a rainbow, but it is a rainbow. This is light from 1200 to 1600 angstroms. So it's the UV light of the quasar. And so what you do is you write a program. I used Python. I did a lot of coding. And I just went down, you go down the line and you measure how bright the pixels are. And you make a histogram of the pixels. And you turn that into this. And there's your spectrum. So this is a spectrum of a quasar observed 3 times over like a 15-year period, roughly speaking. And so you can see, this one didn't change that much, but this is the carbon-4, this is the Lyman alpha again, so we're sticking in the same region. There's an absorption feature right here. It's rather far detached from that carbon-4 emission feature, so that would be a high velocity, something like 25,000 kilometers per second. And the black one is the first one, the first in the series, taken with the Sloan survey. And then in the next one was the red one here, and you see the absorption feature appeared. And then we went back and looked at it with the Gemini Observatory in the cyan color, and it's sort of stayed the same. So I wanted to monitor how these absorption features change so I can try and tell something about what's happening with the wind. Well, here's some data, because data is always fun to look at. It turns out, and this ends up making a lot of sense, but here's a time frame on the bottom. This is time between successive observations, whether it's 1 year, 2 years, 10 years, 15 years. When was your last observation and when's your current one? How long between? And then the above or below 0, right here, this is 0. If it didn't change between those 2 observations, you get a 0. And the positive or negative is just a measure of whether it got deeper, like more absorption or less absorption. And so you can see the longer you wait between your observations, the bigger a change you'll get. If your observations are 2 days apart, those absorption features are going to stay the same. If they're years apart, those absorption features are probably different. Simple check to do. This was a really, really fun one, and it looks a little weird, but let me walk you through it. So this is the wavelength on the bottom, and this is that silicon-4. There's almost no carbon-4. There's almost no, usually they're big peaks. There's like nothing. But remember, the further you go this way, the higher the velocity of the outflow, of the wind that's flying away. And here's the Lyman alpha, and this is the absorption feature we saw. So it was a full, and if you look at the scale on the top here, this absorption feature was almost 60,000 kilometers per second moving towards us away from the accretion disk, which is the highest velocity one we'd ever seen. It's insane for wind to be moving that quickly. To put it in perspective, so 60,000 kilometers per second, the speed of light is what? 300,000 kilometers per second. Like, this is a significant fraction of the speed of light, a whole bunch of wind flying away from the center of a galaxy. It's crazy. That's why these things are fun. Now here's some cool stuff. So this is my favorite one. We got 5 epics, 5 hits on this one. Instead of just 3, we had 5. We got to go back and get some more. So this is day 1, and then there's another one 100 days later from the previous one, and not much is going on. But 750 days after this one, these 2 massive absorption features showed up. Both carbon-4 absorption. One at like 10,000 kilometers per second, and the one further out here at like 30,000 kilometers per second. But you go 66 days later, and then they've almost completely disappeared. At least within our uncertainties, they've pretty much disappeared. And then 300 days after that, they're gone pretty much completely. So you're able to watch a full cycle. This was a regular quasar. A quasar that was normally, if you just picked it out of the sky, was one of that 75%. A regular quasar. Just a quasar. But then, with the continued monitoring, it changed into a broad absorption line quasar. Continue monitoring again, it changed back.
Why?
It's either the gas that was moving towards you was also moving sideways, and so moved off, and therefore was no longer absorbing the light from the accretion disk, or the gas is still moving towards you, but its absorption properties changed, and say its density changed, so it expanded, and sort of the light was able to get through it without being absorbed. Yeah?
Do you think the quasar may be pulsating or rotating? Do you have any evidence that...
Pulsating, no.
Rotating and causing that, or pulsating?
That's a great question. We know that it's not pulsating because the light that's in between the emission features, what I call the continuum light, isn't changing. So that tells you that the accretion disk is outputting the same amount of light. That's a really good question. So when the amount of light is staying the same. So we're measuring the brightness of the quasar to stay similar. Although rotation, because I'm imagining that the accretion disk is at like a fully flat disk, but it could be like a warped disk, and if that warped disk is rotating, then you would go into an alignment where you don't see it anymore. So there are people working on that, and it's not completely ruled out yet, although it's not like the main line of thinking.
Were all those spectra taken with the same instruments?
No, great question. Many different instruments. These 2 were taken with the Sloan Digital Sky Survey's first spectrograph. That was back in the early 2000s. These 2 were taken with the Sloan Digital Sky Survey's second spectrograph when it got turned to the BOSS survey. And then this one was taken with the Gemini Observatory in Hawaii.
So was there a careful job of calibration?
Oh yes. That was like a year and a half worth of work. I didn't even tell you. I did 100 of these, 100 quasars. This is how I went through it. There's survey data that's just public that anyone here can just go look at. And the first 4 actually on this one were already available to me, became available to me halfway through my PhD. And so we could just take the public data and look through these and see this happen. And then I went after this one with my own telescope time. So we went after 100 of them. And all of them that we looked at had something appear, and we were looking to see what happened to it after it appeared.
Could the gas be turbulent as it's coming off?
It's going to be definitely turbulent, but it's also going to be, in order to absorb this much light, and to put it in perspective, it's in a normalized plot, what that means is that this is like as bright as the accretion disk gets, and then this dashed line down here is 0 light, right? And so this absorption feature is absorbing like 30% of the light coming from that section, right? 30% of the light is being absorbed. So it's a really thick cloud, really, really thick, really dense, in order to absorb that much light. So turbulence, they would absolutely be turbulent, but that shouldn't affect just because of the density so high.
Do you think that you have enough data to predict behavior?
We tried to do that. And did I include that? What's my next one? Yes, we did try to do that. Okay, let me see if that, we wanted to see if it had done something, will it continue doing that? Yeah, okay. So, what was that's not this slide. This is something different. Okay, so we had enough, let me answer that question specifically. We had at least 3 spectra for each quasar, and so we could, in one, see that it appeared, and then we could make see if it had happened again in the third one. And then if we had ones that, some of our quasars, we got 4, 5, or 6 spectra, like this one, and we could see how often it continued doing the same thing as before. If it had got more absorbed in one epoch, what was the likelihood that it would get even more absorbed in the next one? Or what's the likelihood that it would shrink and go away? And we attempted to, and our data said that we had no way to predict. And I know, it's the way science works out. Science is always like, oh, this is cool, if this would work, and then you try it, and then it doesn't work. And the reason is probably because we had some quasars where we saw changes happen on timescales of, and massive changes happen on timescales of 10 to 20 days. So you could look at it at one point, 10 days later, and look at it again, and then the absorption feature has changed, which is telling you that it happens on quick timescales, and so, and it's not always going up or down. So basically, it's chaotic. It's clouds of gas doing whatever clouds of gas do, and it's not periodic. It's not something that's going around the quasar. It's not something that's being shot out on a periodic basis. It's a massive, tumultuous, bright thing that's just chucking stuff out at random. And so it's completely random. We did try to predict, but it didn't work. One thing we also tried to do is something in the case of this one, where there's 2 absorption features in the same one. We wanted to see if they did the same things. So, let's go back to this one. This one is a cloud of gas absorbing carbon-4 light at 10 to 15,000 kilometers per second. And this is another cloud of gas that's absorbing the same carbon-4 light, but it's moving at 30, 35, 25, 30,000 kilometers an hour. So they're distinct, but they're both absorbing carbon-4 light. So if it changes, are they going to do the same thing? If I go look back at it, will it do the same thing? In the case of the one before, it did. They both went down and then they both went up. So in our data set, it said that about 67% of the time, if with quasars that had 2 absorption features, they're going to change the same way. They'll get dimmer, or they'll get more absorption or less absorption in the same way. But there's a certain amount, there's about 20% that did opposite things, where one would get way more absorbed and one would go away. And what the heck is going on there? You'd think that it's just one chunk of gas moving out with a velocity range. Some gas moving slow, some gas moving quick, but all moving sort of with the same idea, but they do different things. Some start absorbing more, some started absorbing less. But it's only 20% of the time. The vast majority of the time, the 67, 70% of the time, they are doing the same thing. And that leads us to believe that it's likely that when you see variability, that it's because the gas itself, the entire wind is changing its properties of absorption. It's either getting hotter, or it's expanding, or its density's changed, or whatever. It's not because the gas cloud has moved out of your line of sight and is no longer absorbing. And that we can tell because they usually do the same things. But we can't rule out the other one because sometimes those absorption features vary completely differently. So this is really hard to do. Okay, you want to look at cool pictures now? That was like a really rough rundown of what I did with my PhD. Basically looking at how absorption features change. But 90% of the time, I'm just like sitting at a desk in Toronto, like looking at pictures and writing code and like trying to like make histograms and measure absorption strength and stuff like that. But like 10% of the time as an astronomer, you get to go do cool things. And so these are the places I got to visit while I was doing it, astronomy actively. I got to go to Kitt Peak. Who's been to Kitt Peak? Yeah, a few people. It is the best. It's so fun. You can go there. You can really just like it's open daily, 9 to 4. You can just show up and like go up the mountain. It's a cool road that goes up. A nice high place, 6,800 feet. They kick you out at 4 because the observing starts, but you can go up and hang out. They do nighttime things as well, so you can sign up in advance and like be part of some nighttime stuff and like actually watch or do some observations. But they kick you out at like an hour or 2 after sunset. But that does happen. So the first time I went, I didn't get to go all the way to the top of the mountain. I was at the MDM Observatory, which is about a couple of miles down the mountain. But this was my view. So that was the observatory I was working at, and that's the top of the mountain up there with the big Mail 4-meter telescope. It's a great view. You're in the middle of the desert, just outside of Tucson, Arizona. This was the telescope I was using. I think it was a 1.8 meter. There's me standing under it, so it's pretty big. Woo! That's the telescope, primary mirror right there, and that's the instrument. Well, that's the instrument, and that's filter wheels and spectrographs and stuff. That was a while ago. I had to fill it up with liquid nitrogen every time you go to use it. It's cooled with liquid nitrogen. I have just a crazy story about this. This is like I like telling stories about going to observatories because it's just nuts. So this is me. I can't remember when this was. Oh, it's like 2009, 2010. That's ridiculous how long ago that was. Feels like it was yesterday. But I was really green. Really green. I was an astronomer that came from a school. I came from McMaster University that did my undergrad there. There was no observing program at McMaster. My astronomy was textbook astronomy. I wrote tests. I learned physics. I learned about the universe through a textbook, but I didn't do any observing. And when I started grad school, I started under Patrick Hall, who is like just a prolific observer, and all he does is observe. I didn't know what I was doing. So this was my first observatory that I went to, other than playing around at the one at York, which is a great observatory, but not quite research grade. And I'm supposed to go there at the same time as my supervisor's collaborator postdoc. So 2 supervisors sent their students to an observatory. The other student was much more senior than me, so he was going to show me the ropes, and he's used this telescope before. And like I'm on the plane, and when I land, I get an email saying this guy had dental surgery. He had like some super bad dental surgery he just had to take care of, so he couldn't come. So I showed up to this telescope, no idea what I was doing. And I had to do it all by myself. It was the worst. Not because like, the reason it was the worst is because I felt like every minute that I didn't know what I was doing, I was wasting time. Because, you apply for time on telescopes, and my supervisor spent thousands of dollars to fly me there and put me up for the week and get me to do observations. But my supervisor also stayed on Skype with me till like 3 in the morning, helping me operate it. So he's a pretty good guy. This is what it looks like on the screen, getting test spectra, making sure there's the actual readout from the camera. This is me. I wanted to get a couple pictures of me, what I was doing all night, and literally that's all I did all night. It'd be like, okay, next target, go. And it's like, wait for 20 minutes. They're 20-minute integrations, 20-minute exposures, making spectra. Another funny story, I was on a Skype call with my supervisor's postdoctoral student, Paula, and she was helping me because I had no idea what I was doing. And I was sitting there in this chair just like this, and I noticed like a mouse running around, right? And like, you know, I'm like, oh, okay, oh, there's a mouse, you know, whatever. It's in the middle of the desert, it's on top of a mountain, I don't know. They also warned me to check my shoes for scorpions, so like, you know, a mouse isn't so bad. But I'm sitting there and I'm like doing observations, I'm like sitting and waiting, and then just like this loud, like super loud smack. And like 2 feet away from my feet, it had just got caught in a mousetrap. And it was just like the most startling thing at like 3 in the morning. The worst. All right. Oh, there's the view from the Mayo. So that's the entire mountain. That's the top of Kip Peak. There's like 20 observatories up there. I was down the mountain over this direction a little bit. But I went up during the day and did a little touristy stuff. So this is the view from the 4 meter. That's the 4 meter there. This is another observatory I use called the Bach 90 inch from the Stewart Observatory. That's the size of its primary right there. But this is the 40 meter, and that's the catwalk up there you can go get pictures from. That's the 4 meter telescope on the inside. That's me. You can see it's a pretty big telescope. This was a different place I got to go. This was down in San Diego. This is the Palomar Observatory. That's the 5 meter Hale. One of the largest telescopes on the planet for a very long time, for like 20 years. I got to go down there for 2 days. There's me. There's the 5 meter. The biggest telescope I ever used. I got 2 days on that one. Rained the entire time. Right?
Like Ottawa.
Yeah, it's just like Ottawa. They had a pool table though. This is my favorite trip. I didn't get to do any observing. I applied for a job. So, what was this? This would have been the fall of 2015. I was out of I finished my PhD and I was applying for jobs. And one place I applied was this. This is the Canada, France, Hawaii telescope. So 4 meter telescope out in Hawaii, up of Mauna Kea. Just one of the greatest telescopes ever. And I applied to get a job there, and I got shortlisted to the top 3. So they flew me out there for interviews and stuff. And I got to go up to the top of the mountain and see the telescope. That's on the catwalk. I think that's Gemini behind it, right there. A couple other observatories. It's weird up there. Has anybody been up to Mauna Kea? Yeah, a couple. Yes. So weird up there. Like no vegetation. You feel like lightheaded. It's the highest I've ever been, 13,000 feet, 13,005. And there's under the 4 meter of CFHT. They took me up to take a look. But I didn't get that job, and I got this one instead. So who knows what if I got that job? I might not have been here. All right, that's all I got for you. Thanks, everybody. Any more quick questions about broad absorption line variability? Maybe one? Yeah?
What are your thoughts concerning the mechanism that actually would lift that material out of the accretion disk? Is it something that's related to variability in magnetic fields buried in the disk?
Great. The question is, why is gas lifting off the disk in the first place to get blown away by the light? We have absolutely no idea. And magnetic fields are sort of like that. They are invoked. If you have an ionized gas rotating really quickly, it's likely that you'll have induced magnetic fields.
Right.
We have no idea if that's true, but it seems like it makes sense. And so the answer is nobody's looking at it yet because nobody knows how to talk about it. But you'll see at the beginning of papers, maybe magnetic fields are what's doing this, and then they stop talking about it. So probably that. Yeah?
How has the field progressed since your thesis?
How's the field progressed since my thesis? They have more epochs now. So the Sloan group has been releasing data for 15, 20 years. I use data release 7, data release 9, and data release 10. but they're on 12 and 13 now. And so there's more epochs that I haven't even looked at because I stopped researching. So I probably could add to that one that had like 5. There's probably another one that I could see what's happened since. And that could change what's happened. That could change my calculations. So more data. I guess it's probably good to leave it there. Thanks, everybody.
Leave it there. There's any other questions? All right, time for observation reports. So Jim, you're up first.
Okay, just a quick one. How many people were able to see the super blue blood moon? Anyone? So it wasn't cloudy where you were? No? I didn't even try. I didn't bother to get up early to try to see it because I can't see the west from my place. So I did actually get a good look at the super blue moon earlier in the evening. This was around midnight when it was well placed overhead. This is a mosaic of, I believe, 12 frames. Each frame is the best 10% of 3,000 frames stacked in registacks. Now, showing the whole disk here on the screen doesn't really do justice to the resolution of the image, so I've zoomed in on a couple of different areas of interest. A lot of people might not think that the full moon is an interesting time to observe the moon, but I think that it is. There's a lot of things that you can't see at a part phase that you can see in a full moon. One example is the variation in the colors and the brightness levels, called the albedo of the moon. And it gives you an idea sort of the history of what's been going on, because things that are brighter tend to be younger. They, over time, because of the charged particles from the sun, they get darkened. So if we look at this crater, whoop, what just happened? This crater that is up in the northwestern part of the moon called Aristarchus, it's one of the brightest features that you can see on the moon. It really stands out during the full moon. And I especially like it and this whole area because if you look carefully, there's a diamond-shaped plateau. It's quite noticeably different in color. It's got a reddish-brown color, and it's a volcanic feature. So that's an uplift from a lot of volcanic activity, the most recent of which created Schroeder's Valley. So this was a river of lava flowing at one time that has carved its way through the surface. So those are all really interesting features to try to find and to check out. Moving over to the top right, another thing I like to examine during the full moon is the variation in the color of the mare. And you can see here between serenity and tranquility, quite striking differences in the basalt color. If you were to do a spectrographic analysis, you would find that there's actually different mineral compositions. I believe the bluer has more titanium in it, I think. I'm not sure. Maybe Simon can help with that. But it's interesting to see because it really is emphasized by the sun being overhead on the moon's surface. So it's another interesting thing to check out. One question, this is a quiz for you to go off and try to figure out for yourself. This ejecta ray right here, is it from this crater or is it from Tycho, which sits way down below? Because you can follow this ejecta and other ejecta material all the way back to Tycho, so it's not totally clear where it came from. So it's kind of neat. Of course, Tycho Crater here at the bottom. I especially like this ejecta ray over here because Depending on the light conditions, it has a bit of a bluish hue to it. That's kind of neat. And it really gives you a good perspective of, you know, how violent this impact was. There's a lot of material thrown out. You can also notice quite well during the full moon this dark ring around Tycho. And that is the blanket of melted material that was splashed out of the impact and just kind of flopped down onto the surface of the moon. So it's, if you zoom in, and you can do that with the Lunar Reconnaissance Orbiter, you can see the texture of this material. It looks like it was molten at one time. Well, that's kind of neat. You can actually see that from your telescope. And the final thing that I think is cool to look for during a full moon is go around the rim and look for mountains. So here's a couple that stand out quite prominently along the limb. These are the same image scale, so if this is 86 kilometers across Tycho Crater, that makes that mountain, 5 to 10 kilometers tall, that feature. So it's kind of neat that you can see mountains in that profile during a full moon. So that's it. Thank you.
So it's been a little while since I've had observations, but February was kind to me. Starting off with M67, it's an open star cluster in Cancer, I believe. This is about 2,600 to 2,900 light years away. Sorry, just checking the notes. Yeah, and it was only 2 5-minute subs. Just a quick test of my gear that night. Next is the Leo Triplet, about 35 million light years away. This is about an hour and 15 minutes of total exposures, of 5 15-minute frames, including M65, 66, and NGC 3628. So I took the opportunity before Orion left the season to do another take on this. It's 3 5-minute subs for about 15 minutes. But what was interesting is when I compared it with last year's, I observed a couple of features that just really popped out. And if this will play, the GIF, there we go. There's a couple of variable stars here and here. So, this is taken almost exactly a year apart. And I went online and checked the databases, like Sinbad in particular, and identified the stars. So, V NR Ori is the first one that I identified. It's an irregular variable star. It's probably a young, low-mass dwarf, and amongst the bibliography, I found references to it as a flame star, or a flare star rather. And these can flare up dramatically in just a matter of minutes to hours. And this one I noticed later while looking more closely. Orion actually contains quite an abundance of variable stars, and a lot of them are categorized as Orion-type variables. So while I don't go out of my way to spot variables, I know a few do take measurements of them. When they pop out like this, I thought it was quite noteworthy. Yeah. Okay. And this was a 3-day-old moon, just last February 18th. I noticed really nice Earth shine, so I tried to capture the visual experience in a high dynamic range picture. This is a composite of 7 different exposures and then superimposed on one as a background there. So, yeah, thank you.
Hi, I have, not anymore, I guess.
Just hit the green button, the play button.
There we go. I had an opportunity to take some pictures 2 and 3 weeks ago when conditions were favorable, again from the Palomar Observatory. First it was promising, was -6, -8 temperature, then a little bit colder when we got there, and then by the end when we were leaving, -27 again. So, however, it had a good influence on clarity and darkness and stability of the pictures, so this turned out to be not too bad for M1, which was getting pretty low. So M1 is, as you know, the remnant of the supernova explosion. It's a nebula consisting with all the debris which were left from the explosion, with a fearsome 21-kilometer diameter pulsar in the middle, rotating at a crazy speed, 30 rotations per second. There is lots that was said about it in the previous observations, so I will not be getting into the details, just mention that this is an amazing object and it's widely used by many astronomers for calibration purposes, for studies and so on. The next picture is 2 weeks ago, again, FLO Observatory, M82 or Cigar Galaxy. This constituted about 2 hours of exposure. What I wanted to achieve was these little traces of hydrogen gas shooting from the either side of the galaxy. As you can see, as you know, this is the edge-on galaxy. I've heard it was disturbed by some smaller galaxy passing by, so it's not really absolutely a regular form, it's a bit kind of curved. And these jets of hydrogen gas being ionized by the stars, they can be prominently seen emitting red light, especially on the Hubble pictures. This is a little bit noticeable here, but apparently it's not possible to get as clear pictures from the ground, from Earth, as Hubble can do that from the space, of course. The M101, it's a galaxy size roughly of Milky Way, and it's a beautiful object as well. The core of the galaxy is about 30 billion sun masses. The distance about 20 million light years away from our galaxy, and you can clearly see how it rotates the arms. Some objects inside that galaxy, like a nebula, I managed to run a software which does the plate solving, so it reported a few of those NGC objects. I googled some of them, and they are mostly reflection nebula, like this one, which means that the light from the stars inside is getting absorbed and reflected rather than excited and emitted, as in some cases. I believe that those are bluish ones are reflection nebula, and the reddish ones are emission nebula. It's just amazing to see that the same objects which we have in our galaxy are common all across the universe. Thank you.
Not my slide.
You got there's a clicker right on the...
Oh, I usually mess that up.
Big play button. There you go.
I'm so forgettable, my name wasn't even added to the various menu tonight, but that's okay. Just before I get to the Lunar Eclipse slide that I'm showing tonight, on Paul Comision. Paul gave a great lecture about his great ideas in astronomy. He showed many of the great images toward the end of galaxies. It's funny, when I was meeting chair at the Canada Science and Tech Museum, I remember Paul would sit on the far left over here. One night he's like, computers, who needs them? Who bought a CCD camera and a laptop? Paul did. Like a kid in a candy shop, had what, over 900 images he had to choose from? It was great to see that. So here we have the only lunar eclipse I had on the day in question about a month ago. I was on 13 radio stations across Canada, including the Vancouver Courier, the SBBN, Super Blue Blood Moon. Ooh, that media went crazy on that. What does it mean? What does it mean? So I went through the various letters of the acronym and mention what it is, and then mention that in February we don't have a full moon. Well, that even got crazier. How is that? Well, with the Metonic rate of every 19 years, which we'll get in 2037, January will have 2 blue moons, March will have 2 blue moons, February won't have. So they went nuts on this. So it was great to get on air, mostly to publicize a wonderful lunar eclipse, which the West Coast was going to get the best show. And as Jim mentioned, we do for Astronomy Day, the various volunteers that hopefully to edge on the young people, and old people to astronomy, but most of the younger ones, which I love to do, which they stay with science, which will probably add to a huge discovery in 20, 30 years. That started from that one eclipse. So on the morning question, Joe Bonner went to the Via Rail station in Barrhaven. I was hoping that the moon would get lower and clearer, but unfortunately it was going through clouds, so this was the best shot that I took. Did anyone see the moon? Sorry, the moon on Wednesday morning? Just hitting the horizon, there was no cloud at all. Too bad it didn't have, but that's the money shot for now. So for those that just see the eclipse, I hope you enjoyed. Another 10 months now until we get the next one. It'll be winter, but Ottawa will have the ringside seat for the whole eclipse. So thanks for your attention. Have a good night.
Thanks, Gary. All right, so I've got a couple images that Mike Worth's submitted to us all the way from Baja, California. So this first one is of the Plato area. So actually all his images there were taken with an 18-inch star-structured Dob with an ASI 174mm camera using a 4 times Barlow lens and a red filter. So this is the Plato area. It's pretty fantastic, the resolution that he gets down there for these images. This one is Clavius and Tycho. And the last one is Copernicus. Cool stuff. Thanks, Mike, for submitting that.
Oscar, can you go back to Plato?
I can.
It's really important to point out that coming to the lower left from the main crater, you can see that beautiful rill. It's a valley. But if you follow it down, just before you get to the edge there, it suddenly disappears, and then it reappears again. And that clearly is evidence that that was a lava tube, where the roof has collapsed over where you can see the visible valley, but the lava tube roof is still in place where the valley appears to be interrupted. And it's incredible that he managed to pull out all that much detail in that photo.
How big do you think that feature is in that width of the rill?
It's kilometers across, which is huge for a lava tube.
Okay. Thanks, Simon. Ooh, did not look like that when I was processing. So this is the Ring Nebula with a lot of noise. So this is about 55 minutes of data. It's taken through an 11-inch Edge HD, 1600 ISO through using a Canon 60DA. Hopefully the rest of my images don't look like garbage. We'll see.
Nice pulling out that galaxy, though.
Yeah, so that's IC 1296. All right. Yeah. Projector. So this is the Crab Nebula as well. What Taras showed earlier. It's 3 hours of exposure, same scope, the 11-inch HD at f10, 1600 ISO, Canon 60DA.
What's that glow in the lower left?
The glow in the lower left here? I'm not sure. Anyone know?
Amplo.
I think it's Amplo. It would probably show up in this image too if it was Amplo. Okay, my last image is the Leo triplets. So this one's through my 80mm apochromatic at f5, Canon 60DA as well. And I picked up a couple small IC objects in there as well, IC 2745 and IC 2702. That's it for me. one in February was clouded out, I believe. There's one coming up on March 17th. And I'm told there's going to be beer served. Is that true, Gordon? For St. Patrick's Day?
News to me.
Estelle's pick of the month is the red planet Mars. Membership, if you're not a member of the club, please join us. You get access to our telescope library, to the observatory, our book library, various RASC publications. These are the folks that help run the club. Recordings of previous meetings are available on our website, and this one will be on the website eventually as well. So we have an audience of 93. Thank you to everyone that presented and everyone that attended. Post-meeting meeting will be at Gracie's. I called them this afternoon to confirm that there was no live band there tonight. Next meeting is April 6th, and we're having Dr. Andrea Lobel come and present. Sorry, I just forgot a note here that I had on her presentation. Her talk is going to be... Uh-oh, I've lost it. It's titled Gods of Stone and Sky, Mesopotamian Astronomy and Celestial Myth. So that's coming up April 6th. And door prize time.